Hello everyone, welcome back to Power Quality Lecture Series. In this video we are going to discuss about uh, electromagnetic interference and its frequency classification, what the basics of electrical fields, magnetic fields, and some of the EMI electromagnetic interference terminologies, etc. So, all of you know that electricity and magnetism are interrelated and exist in a complementary fashion. Any conductor carrying electrical current has an associated magnetic field also. So, a magnetic field can induce voltage or current in a conductive medium exposed to the field. So, electrical circuit are carriers of electricity as well as the propagators of magnetic field. So, in the area of power quality, the useful properties of electromagnetism are not a concern. Rather, the interest is how electromagnetic phenomena affect electrical and electronic devices in an adverse manner. So, the effect of electromagnetism on sensitive devices is called electromagnetic interference or EMI and is rather a complex subject. So, this table shows how frequency spectrum is classified and their primary use of each type of frequency. You can see that in this table you can see ELF, which is extremely low frequency. That is the frequency range from 3 to 30 Hz. The applications are the detection of buried objects. Then SLF is a super low frequency, that is between 30 to 300 Hz. Applications are communication with the submarines, electrical power. Then ULF is ultra low frequency, that is between 300 to 3000 Hz. That is the telephone audio range. Then VLF is very low frequency, that is between 3 to 30 kilohertz. Applications are navigation. Then LF is the low frequency, that is range 30 to 300 kilohertz. Then MF is the medium frequency, that is 300 to 3000 kilohertz. That is used. Applications are amplitude modulation, maritime, radio, etc. Then HF is a high frequency, that is 3 to 30 megahertz. That is shortwave radio, citizen band, etc. VHF is that is very high frequency, that is between 30 to 300 megahertz. That is applications are television, FM, police purposes, mobile, etc. UHF is the ultra high frequency, 300 to 3000 megahertz. Radar, television, navigations are applications. SHF is super high frequency, that is 3 to 30 gigahertz. That is radar, satellite applications. Then EHF is extremely high frequency, that is 30 to 300 gigahertz. That is used for radar and space explorations. So these are the some of the frequency spectrum and its usage. So one advantage of knowing the frequency band used by any particular group or agency is that once the offending frequency band is determined by the source of EMI may be we can accurately determine the source of EMI. if we know this kind of frequency spectrum. Then we move on to some basics of electrical field. So two important properties of electromagnetism are the electrical and magnetic fields. So an electrical field is present whenever an electrical charge Q placed in a dielectric or insulating medium experiences a force acting upon it. From this definition, we can conclude that the electrical fields are forces. So the field exists whenever a charge differential exists between 2 points in a medium. So the force is proportional to product of two charges and inversely proportional to the square of the distance between 2 points. So suppose if two charges are Q1 and Q2 are placed at a distance of d meters apart in a dielectric medium with a relative permittivity equal to epsilon r, the force acting between these two charges is given by Coulomb law, that is given as F is equal to Q1 Q2 by epsilon 0 epsilon r d square. And you know that epsilon 0 is the permittivity of free space and is equal to 8.854 into 10 raised to minus 12 farad per meter. And if the medium is free space, then epsilon r is equal to 1. Then two quantities describe the electrical field is electrical field intensity. Usually it is denoted as E, and electrical flux density D. Electric field intensity is the force experienced by a unit charge placed in a field. So a unit charge has an absolute charge equal to 1.602 into 10 raised to minus 19 Coulomb. So therefore E, electric field intensity, is written as F by Q. Where Q is the total charge. So unit thus become Newton per Coulomb or volts per meter. Then electric flux density is the number of electric lines of flux passing through a unit area. So if psi number of electric flux lines passing through a unit area A, then electric flux density is written as D equal to psi divided by E. And the ratio between electric flux density and electric field intensity is the permittivity of free space epsilon r. So here you can see that electrical lines of flux between two charged bodies. A charge placed in the field will experience a force known as the electric field intensity. Then a magnetic field. So magnetic field exists when two poles of the opposite orientations are present. The north pole and south pole. Two magnetic poles of strength M1 and M2 are placed at a distance of d meters apart in a medium of relative permeability equal to mu r will exert a force F on each other given by Coulomb's law. That equation is given as F equal to M1 M2 divided by mu 0 mu r d square, where mu 0 is the permittivity of free space, that is equal to 4 pi into 10 raised to minus 7 Henry per meter. And magnetic field intensity, H, is the force experienced by a unit pole placed in a magnetic field, that is given by H equal to F by M. And here you can see that a magnetic flux lines due to a current carrying conductor. So a magnetic pole placed in the field will experience a force which is known as the magnetic field intensity. And magnetic flux density B is the number of flux lines per unit area, that is given by phi by A. In a linear magnetic medium undistorted by external factors, mu equal to mu 0 mu r, and mu r is a relative permeability. So we can write mu is equal to B by H, or B equal to mu H. And we move on to some of the electromagnetic interference terminologies. And here we are going to discuss several terms that is unique to electromagnetic phenomena and not commonly used in other power quality issues. So the first terminology, decibel, that is a decibel is used to express the ratio between two quantities. The quantities may be voltage, current, or power. So for voltage and currents, dB is equal to 20 log V1 by V2 or 20 log I1 by I2. And for ratios involving power, dB is equal to 10 log P1 by P2, where P is the active power. And for example, if a filter can attenuate a noise of 10 volt to a level of 100 millivolt, then voltage attenuation is V1 by V2 is given as 10 by 0.1, that is 100. In dB it is attenuation 20 log 100, that is 40. So second terminology is radiated emission in connection with electromagnetic interference. So radiated emission is a measure of the level of EMI propagated in air by the source. So radiated emission requires a carrier medium such as air or other gases, and is usually expressed in volt per meter or microvolt per meter. Then conducted emission. Conducted emission is a measure of the level of EMI propagated via a conducting medium such as power, signal, or ground wires. So conducted emission is expressed in millivolt or microvolt. Then attenuation. Attenuation is a ratio by which the unwanted noise or signal is reduced in amplitude, usually expressed in decibel. Then common mode volt rejection ratio, that is CMRR. So this common mode rejection ratio is a ratio which is usually expressed in decibel. This is a ratio between the common mode noise at the input of power handling devices and the transverse mode noise at the output of the device. So common mode noise is always is the signal that is between the line and to the ground. Transverse mode is in between two lines. You can see in this particular figure, illustrates the distinction between two modes of noise. Common mode noise is typically due to either coupling of propagated noise from an external source or a ground potential, and it affects the line and neutral wires of circuit equally. And you can see transverse mode is in between two lines. Then noise. Electrical noise or noise, simply noise is unwanted electrical signal that produce undesirable effects in the circuit in which they occur. Then you can move on to common mode noise. Common mode noise is present equally and in phase in each current carrying wire with respect to a ground plane or circuit. Common mode noise can be caused by a radiated emission from a source of electromagnetic interference. Common mode noise can also couple from one circuit to another by inductive or capacitive means. And this lightning discharges produce common mode noise in power wiring. Then transverse mode noise. Transverse mode noise is the noise present across the power wires to a load. The noise is reference from one power conductor to another, including a neutral wire of the circuit. You can see in this particular figure, which depicts the common and transverse mode noises. So transverse mode noise is produced due to power system fault or disturbances produced by other loads. You can see the transverse mode noise can also be due to conversion of common mode noise in a power equipment or power lines. Some electrical loads are also known to generate their own transverse mode noise due to their operating peculiarities. In this figure shown, you can see the common mode and the transverse mode noises. The common mode noise is measured in between the line and ground. Transverse mode is measured in between two lines or neutral. Then bandwidth. Bandwidth commonly refers to a range of frequencies. We already explained some of the range of frequency in a table in the previous slide. So, as an example, a bandwidth of 300 kilohertz to 300 megahertz is assigned to radio broadcast and marine communication. And any filter intended to filter out the noise due to these sources must be designed for this particular bandwidth. Then filter. A filter consists of passive components such as R, L and C to divert noise away from the susceptible equipment. So all these things are discussing or relating to EMI only, electromagnetic interference. Filters may be applied at the source of the noise to prevent noise propagation to other load present in the system. Also, filters can be placed at the load side also to protect a specific piece of equipment. And the choice of the type of filter would depend upon the location of noise source, also the susceptibility of the equipment and the presence of more than one noise sources. Then shielding. So a metal shielding or metal enclosure or a surface intended to prevent noise from interacting with a susceptible piece of equipment. A shielding may be applied at the source or at the equipment itself. So here you can see in this figure to illustrate the two modes of shielding. The next discussion is about power frequency fields. So power frequency field falls in the category of super low frequency fields and are generated by fundamental power frequency voltage and current and their harmonics. So because of the low frequency content, these fields do not easily interact with other power control or signal circuit. The power frequency electrical fields do not easily couple to other circuit through stray capacitance between the circuits. Also, the power frequency magnetic field tends to be confined to a low reluctance path that consists of ferromagnetic materials. And power frequency currents set up magnetic fields that are free to interact with other electrical circuits and can induce noise voltages at the power frequency. And in a power circuit, a magnetic field caused by the current in the supply and the return wire essentially cancel out outside space occupied by the wires. However, the magnetic field can exist in the space between two wires. And here you can see that a magnetic field due to supply and return wires. So the residual magnetic force introduced or attributed to power wiring is rarely a problem if proper wiring methods are used. And the net EMF outside the conduit with a you can typically a power wiring to a piece of equipment is self-contained with the line, neutral and ground wires all are installed within the same conduit. So the net EMF outside the conduit with this arrangement is actually negligible. And once the power wire enters an enclosure containing sensitive devices, the special care should be exercised in the routing of the wires. Here you can see one equipment wiring to minimize the coupling of noises. High frequency interference. So the term EMI or electromagnetic interference is commonly associated with the high frequency noise rather than our power frequency. So which has several possible causes. Some high frequency EMI sources are radio, television, then microwave communication towers, marine or land communication, atmospheric discharges, radio frequency heating equipments, adjustable speed drives, fluorescent lighting, electronic dimmers, etc. So these devices are produce interference ranging from few kilohertz to hundreds of megahertz and perhaps higher values. Due to their remote distance and because electrical and magnetic fields diminishes as the square of the distance from the source, the effect of several EMI sources are rarely experienced. But for locations close to the EMI sources, the condition could be serious enough to warrant caution and care. So this is why some of the agencies like a Federal Communication Commission (FCC) have issued a maximum limits for radiated and conducted emission for data processing and communication devices using digital information processing. Here you can see that common electromagnetic interference sources in a pictorial representation: radio, TV broadcast, communication, then atmospheric discharge you can see, then high voltage power lines, etc. And another figure shows the location of ground plane or wire, which can affect the noise pickup due to effective grounding loop area. So that is about high frequency electromagnetic interference.